The Necromancer's Tale is a full-blown crpg with heavy branching narrative and turn-based combat. It involves deep technical work in many places, including the branching narrative, the development of a scripted cutscene system, which synchronises the 3D world with the text of the narrative, NPC movement and pedestrian simulation, and underlying technical systems which aimed to optimise player experience. We used the tool Artisy Draft to develop the branching narrative, 400,000 words in total. This includes variables and logical tests on them as well as player choices. Artisy exports a pretty complex JSON file, and my work included writing an entirely bespoke importer and player in order to present this to the player. This includes logical tests, variables parsing, flow of control, etc. I decided to write my own importer rather than using the Artisy Player DLL so that I had full control and could deeply integrate the narrative with the actions in the game world. It allowed me, for example, to test forward from any point in the narrative to see if any text nodes had not been visited, or whether any special skills were tested anywhere within a particular branch. This allows me to provide feedback to the user. Fully visited branches are shown in a dimmed colour or hidden entirely, and the places can be highlighted at which skills have changed your options. It means I could also add adjacent subsystems, such as my Artisy variable monitoring system, which triggers in-world events when specific Artisy variables change in value. Another pretty complex system in the game is my cutscene system. I developed a JSON-based format through which I could drive actions in the world, e.g. characters moving around or looking at each other, with special effects, e.g. screen fades, camera movements, audio effects, all synchronized with the text flow in the narrative. At various times the cutscene actions need to wait for a certain text node to play, or jump to a different spot based on player choices. At other times the narrative window needs to pause and wait for an in-world cutscene action to complete, e.g. waiting for a character to finish walking to a specific position in the world. To reduce initial load time for the game, all building interior and underground locations are implemented as prefabs using Unity's addressables system. Using addressables is necessary so that the prefabs are not referenced anywhere in the main game scene, because if they were, they would be stored as part of it. The game overworld, however, is one single scene. I wanted to avoid scene switching during play, as Unity is notoriously slow at doing this. What this means, though, is that any interactive objects, such as world location markers or chests and other inventory containers, are initially not known about when the game starts. My save game system therefore assigns a unique ID number to each interactive object, and the data for the objects, e.g. the current contents of a container, are stored as arrays of bytes, ready for whenever the player first loads up the interior with that container in it. So the save game file is not fully deserialized when you load it. Parts of it have to be held ready to deserialize when their object is actually loaded into memory. Both in-combat and out-of-combat movement uses a hex grid with the A* algorithm. My code for building these starts from a seed position, which is manually set at a walkable location, and then it searches in all 6 directions using raycasts to see which ways can be walked from this location, i.e. which directions are clear of obstacles. This adds more hexes which are then also searched. We flood outwards until all reachable hexes within our predefined region have been added, along with their connectivity to their neighbours. All A* grid loading and pathfinding is performed by multiple threads. A* is a pretty elegant algorithm for efficiently finding the shortest path between 2 locations. At its core is a calculation f equals g plus h, which estimates the distance that a possible solution might take through a given node. The g part of this is interesting. It's the cost of getting from a node to a neighbour. Often this is simply chosen as Euclidean distance between the nodes, but it doesn't have to be. We can make the g cost higher, for example, when crossing difficult terrain. This discourages the algorithm from picking a route without actually forbidding it. I quickly found that the townsfolk loved taking a shortcut through a graveyard, which was often a slightly shorter way of crossing the river between north and south of the city. This didn't feel right. The graveyard path is visibly narrow and not well worn and crosses a narrow bridge, while the standard route is a wider stone bridge leading through the marketplace. So I added penalty areas, regions of space for which the g-cost between hexes is artificially inflated. The graveyard is an obvious place where this works well, but this approach lets me fix other areas too, for example narrow gaps between pairs of houses. I also added a per terrain texture penalty, so that NPCs tend to walk on cobblestones in preference to grass or sand. This stopped them from taking shortcuts all the time, and kept them to routes that they should visibly be using. To have pedestrians move about believably, i.e. not walk through each other, I implemented the reciprocal velocity obstacles algorithm, which simulates characters and other obstacles as moving volumes of space, projecting a couple of seconds into the future to identify likely collisions and have the pedestrians adjust their paths to avoid them in a believable manner.